Okay, hi everyone. Welcome to Blockchain at UBC monthly talk. This will be the last talk for this academic year. That's why we've decided to make it slightly different. It will be in the so-called Fireside chat. For those of you who are new to blockchain at UBC and will a research center focusing on interdisciplinary research related to blockchain. As you will see right from today's talk, it's kind of in the intersection between blockchain technologies and quantum technologies, in particular, some quantum safe cryptography. Today, since this is a new format, fireside chat, we will have two parts. Part one will be led by Hassan, and who will present our very recent work called SILMARILS. Right, for Hassan, you can easily find his background at blockchain at UBC website. He's one of us, and that's why I want to save time. I don't want to introduce further. Just check our website. Then after part one, we will have Q&A between Mina and me, right? For those who want to know more about Mina, just check our previously monthly talk, comprehensive bio, right? And for audience, if you have any questions, you don't need to wait until part two, right? Feel free to ask your questions even during part one. So part one, the purpose is to help you understand the basic ideas, right, and the main functionalities of this new type of digital signatures. And part two is to maybe push it further, right, to clarify some potential misunderstandings. Because this type of construction is so new that we already received some messages due to misconceptions. That's why we thought it might be a good idea for us to clarify things, right? To help our both online audience and then later on we will post it to YouTube, our YouTube audience, and to avoid some potential misunderstandings. Okay, without further ado, let's invite Hassan, please.
Okay, thank you, Dr. Frank, for a nice introduction, and good morning, everyone. And thank you for joining this fireside chat at blockchain at UBC. And today I'd like to walk through SILMARILS, which is an information-theoretic, quantum-aware, designated verifier authentication for ledger. And this work is headed to a selected areas in cryptography or SAC 2023, and it's still under review. And please interrupt anytime because this is meant to be a conversation, not a lecture. So feel free to ask your question anytime you had. So let's give you the talk roadmap. So to give you a map of where we're going to today, we'll cover 5 blocks: motivation, background, the construction, the security analysis, and the blockchain application. So before we get technical, let me answer the obvious question. What is SILMARILS? And for the first time, I spell the acronym. SILMARILS it stands for secure information theory leverage mechanism for authentication and receipt integrated lightweight signature. So it's a very long name. And it we also borrowed a story from Tolkien's book, the Silmarillion, and for the ones who are interested to the fiction movies like Lord of the Ring, and this is actually returns for the times very it is related to the time very before the Lord of the Rings. So if you read the book, you understand what I'm saying. So in the Silmarillion, Fëanor, who was one of the most powerful elves, crafted three hollow gems from two trees, and it bound the light of those trees in a virtually undestroyable form, and they were fiercely guarded, and they could never counterfeit. So our three-party scheme mirrors that triad. Signer, holder, and verifier relay the authenticated flame, and very similar to the three Silmarils intended to do. So this is a very nice coincidence to having this connection to for our scheme. And so let's start with why this matters. And we know that post-quantum migration is real, but most permission ledger authentication is validator local, not publicly verifiable. The hook for today is very simple. Pick the primitive that matches your trust boundary, not use one thing for every purpose. So this is the intention of designing Silmarils. So to make that concrete, we first must know where does authentication actually live in blockchain. So validators verify most traffic, and yet PQ migration often puts multi-kilobyte public signatures on every hot pass. And ask yourself this question: which message truly need anyone to verify signer origin? And also, in which situation you need validator acceptance alone? So auditors may still need something for checking later, like something like receipts. But that's a control channel, not a public PKI on every packet. So that's the rationale behind designing Silmarils, and why we are focusing on designated verifier signature, not general purpose signature. So the pressure shows up sharply when you look at signature sizes, and at 256-bit security, a Silmaril signature is just 160 bytes versus 2420 bytes for dilithium 2, and it is roughly 15 times smaller. So smaller here is not automatically better. It matters when designated verification is enough for the layer you are securing. So in other words, nothing is free. So when you want to shrink your signature, you definitely should pay or release something. So something that we decided to release is public verifiability. So this is the main story. And so let's look at this signature size comparison. So here is the same story in one table, key signature side by side. And the column I want you to focus on is verifier. So SILMARILS is designated plus receipt, and dilithium, falcon, and sphinx are public verifiable, and also look at the size of the signature as well. So it simply indicates that efficiency matters only where transferable designated verifier semantic fits. And this also indicates that PQC migration is not just dropping lithium replacement or used some PQC scheme everywhere. So you should be smart and see everywhere and select what fits appropriately. So this is what we want to do. And so yeah, let's see what information theoretic security means here. So uh, and somebody may ask, why bring information theoretic security into a blockchain talk at all? The answer is very simple. The algebraic core needs no factoring, like LW, learning with error, or isogeny assumption. So the information theoretic security tools are very simple, unlike the tools we usually use in public key cryptography. So that's why we decided to use information theoretic tools. So there is also a classical limit, and a plain IT signature over noiseless channel alone cannot bear error more than error 1/3. So we use designated verification and in three-party mode authenticated channels to reach error 1/p. So it's very simple. If you want to design IT signatures from scratch, then you must have the error greater than 1/3 and over noiseless channels. So this simply indicates that this is not that easy. So, and this is also a non-trivial problem. So you cannot have something very similar to public key encryption, public key signatures, and have all their good features, and only based on information theory. So this is like something like a no-go theorem. So so what you actually can have to get rid of this lower bound on epsilon is moving to the transferable designated verifier instead of public verifiable schemes. So given all that, here's how we respond. And I want to be clear, we are not offering less security, but a different goal. So SILMARILS trades public signer origin proof for compact validator authentication and optional receipt-based audit. So in our scheme, two-party mode uses ROM or QROM analysis, and and ROM and QROM appear here because we have some application of hash functions in our scheme. So that's why we need to model them using the random oracle model or quantum random oracle model in the security analysis. So that's what connected us to the ROM and QROM. So And our three-party mode is based on the design of three-party digital information-theoretic digital signature, which is proposed by Fitzi, Maurer, and I don't remember the third name. By three people, I just named two of them. So our three-party mode is based on the well-known Fitzi and others models. So this is the term that we use for the security notion in the three-party setting. So pulling the motivation together, the paper that we submitted and this presentation contributes four things. The first one is a concrete transferable designated verifier scheme with 160 byte signature. Second is a three-party variant, secure in IT, information-theoretic, RAM and QRAM. And third, we generalized the Fitzi model to the quantum setting because it was based on a classical assumption. So we generalized it to quantum setting and to be able to model quantum queries. So the thing is that our proof is not based on forking lemma or rewinding techniques, which usually break when you move to the quantum setting. And we also provided a blockchain reference architecture in ROS to show the application of this scheme in the blockchain scenario. So this is our contribution in a glance. And now let's turn to the background. And before going to the background, we might ask that where does SILMARILS sit among signature families? At the high level, SILMARILS is not trying to be the one signature scheme for entire internet, and it targets validator-centric, high-frequency authentication in permission system with optional receipts for governance and audit. So this is the position of SILMARILS. And in this busy mind map, you can see different families of digital signature, lattice-based, multivariate, isogeny-based, code-based, hash-based, classical, and the information-theoretic one. And you can see here the Fitzi scheme sits here. But in this busy mind map, is really there is something that really making one point. Classical PQ and Max, designated verifier, and IT primitive solve different problems. SILMARIL sits at the intersection of an IT core with designated verifier semantics. And when you need it, you can combine it with the three-party information checking scheme. So SILMARILS can be considered as a combination of this mind map and also another mind map that focuses on designated verifier digital signature. So that's the that's why that's because we have two. So something that we have provided here is assuming a three-party mode that relates SILMARILS to the information-theoretic signatures. So this was the a reminder about the classification of digital signature. So The idea that trips people up most often is designated verification uh, enough for what the first question might be, first of all, what is the designated verifier intuition? And this notion introduced in 1996 by Jakobsson, Sako, and Impagliazzo, and it is based on a simple thing. Alice wants to prove that either a relation phi holds or I am Bob. And Bob, as a designated verifier in this scenario, is convinced, and Cindy cannot tell who signed the message or who created the relation feed. And in the meantime, Bob can simulate valid transcripts. So Cindy cannot understand which transcript is generated by Alice and which one is generated by Bob. So, in the first look, it might seem something like a weakness or bug in the system, in this design, but this is not the case, and we realize it soon. So the natural question follows, is this just a Mac? So the next question that we usually are asked about SILMARILS is the designated verifier just a Mac? So the answer of this question is no. If you look at the comparison of Mac and public key digital signatures and transferable designated verifiers scheme like SILMARILS, you can see that in the Mac, the person that verifier is the secret holder. And in the public key encryption scheme, it is anyone. And the Mac is not transferable, so you cannot delegate your verification capability to other people. And in the TDV scheme, you can transfer your verification capability by publishing the receipt R. And the public key schemes are definitely publicly verifiable and totally transferable. And and also, there is another feature that is a verifier simulatability that Max cannot provide you that, TDV provide you that, and Dilithium cannot provide that. And the use of the information-theoretic core in the Mac and TDV is in common, but the public schemes are using different language here. So these are the main difference between TDV Max and public PQ signature. And when you need more than a pairwise TDV, we add a three-party mode, and it helps to state ideal goal first. The functionality FDS is formed by two-part FDS1 and FDS2, and it splits into sign, then transfer, and followed by verification. The signer outputs sigma alg, as you can see here, and um, and and also extracts x1 as the hash of message and sigma, and the verifier outputs z3 as x1 or bot. And in ledger terms, signer, holder, or relay are validating are behave like relay for validating a signature. So this is the the parties and how they are connected to each other and how they interact with each other. And we have also three security models here. So in the pure IT setting, we model the hash functions as injective functions to finite field FP. So here we just look at the hash function as an injective map. And we call this security model as a pure IT model. And if we add an oracle to this model, we reach to the IT plus ROM. Here we just use the classical random oracle models. And if we add quantum queries, we need QROM, so we reach to the model IT plus QROM. So these are three different security models, their assumptions, and their definitions. So, all right, let's build SILMARILS. I'll fix notations here. So sigma alg, it stands for sigma 1 to sigma 5. Three-party information checking uses X as the hash of M and sigma alg. And we have also a tag of the form sigma tag equal to K1X plus K2. So please do not confuse sigma alg and sigma tag because they look very similar. And so, yeah, the algebraic building blocks are explained in this slide. And you can see that everything lives in FP, and we assume P at the order of 2 to the power of 256. We have a long-term secret key K, and we have a pairwise key K-sig that can be derived from the TLS session key. And SS22 stands for Shamir secret sharing with two shares and with threshold 2. And we have two public weights, W0 and W1. K prime is the ephemeral key, that is the HMAC K of M, and N is the nonce that is generated from M and using the session key K6. And the receipt is just the hash of M and nonce, and H is just a hash function from 0 and 1 star to FP. And the algebraic signature is just sigma 1 and 2 sigma 5. So we have first in the key generation, we first use a TRNG to generating the public weights and secret key, and we use TLS for TLS session key for generating K-sig, and we also choose the prime P and sample W0 and W1 using our TRNG. Yeah, so everything seems to be very easy and natural. So signing itself is just a short pipeline. Message M goes into the protocol. HMAC, we apply HMAC, and we do some sampling, and we do some Shamir secret sharing, and we form sigma alg by employing 10 to 12 field multiplication, and you will see the equation soon. And we also generate the receipt from nonce and the message. So the signature equation are summarized in this slide. So we sample B, D, alpha, and beta from FP star. We set epsilon as alpha, beta, and The Shamir shares are ki prime equal to k prime plus akwi. Definitely we have two shares, so k prime 1 and k prime 2. And we also do the Shamir secret sharing on epsilon. So we have epsilon i's in this form. And using this equation, we define sigma 1 as b times k prime minus r. R is the receipt. And sigma 2 as d b inverse, and sigma 3 as k1 prime d, and sigma 4 as d epsilon inverse epsilon 1, and sigma 5 as d k 0 prime minus r epsilon inverse epsilon 0. So these equations are the algebraic definition of the signature components. And also, you do not need to memorize the formulas. Just remember the punchline and look at them just as 5 field elements, one receipt and one zero test for verification. So this is the whole story. So the verification pipeline is even simpler. So we recompute n and r. We reject if sigma 4 is equal to 0. We form sigma v0 and v1 as sigma 1, sigma 2 minus sigma 5, and sigma 1, sigma 2 minus sigma 3 plus r sigma 4. And after forming v0 and v1, we accept the signature or confirm the verification if v, which is defined as the inverse of Shamir secret sharing with two components, v0 and 1, gives us the constant value 0. So if this is equal to 0, then the verification is successful. And stepping back from for a moment, here is what that buys you in size. It gives you 32-byte secret key, 64-byte public key, and 160-byte signature. And that's roughly 6.6% of the dilithium signature. And also the verification cost is very reasonable compared to other signature schemes. And somebody may ask that why that accept rule is correct. So the question is very simple. An honest signature places V0 and V1 on a hidden line through the origin. And Shamir reconstruction is essentially testing whether f of 0 is equal to 0. So this is very simple idea for checking the verification. And here, any forgery will be distributed as a uniform random variable, and it will be rejected with probability 1 minus 1 over p. So it indicates that the probability of rejection in this scheme is 1 over p, which is negligible. And the same sigma alg, here we want to jump to the three-party mode. So we use again the same sigma alg, and we use the value x as the h of m and sigma alg, and we also have a tag here as k1x plus k2 with secret k1 and k2 at p3. So these secret values are only known by P3. So if P1 computes sigma alg, then it computes X, and using the information checking protocol proposed by Maurer and Renner, it can authenticate X, and P3 can check the sigma tag is equal to K1X plus K2 by knowing the values of K1 and K2. So by receiving the value of X, it can easily check the equality of the provided tag with the tag that it can expect from P1. So this is the signing phase of uh, the uh, the the three-party. And we also have a transfer phase. So once that IC phase complete, transfer is simpler. The holder sends X and sigma tag. The verifier checks the line and outputs Z3 as X or bot. Okay, zooming out, you will see here one algebraic core and two wrappers around it. So two-party TDV under ROM and QROM, and three-party information checking with error 1 over P. And we don't want to prove a reduction between these two modes. You choose the one that fits your trust boundary, and that completes our construction. So the next comes security, where this TDV often surprises people. So let's talk security. And the single most important security message is on this slide. So DV simulation is not is a feature, not a bug. Anyone who knows R or seed can forge an accepting sigma alg star. And without the and that's happening even without knowing the signature, the signer's long-term key K. So the designated verifier can do this because they hold K-sig. That's exactly the Jakobsson and his colleagues' property. Only the designated verifier simulates, and outsiders still cannot tell a signer from validator origin. So that's it, actually a nice feature that somebody cannot easily the parties that know R can forge accepting, but the other people cannot do that, and also cannot tell the difference between these two scenarios, that this signature is generated by a simulator or by a real person.
Oh yeah, hi Hassan. This feature is very interesting, right? So
Yeah,
just to clarify, it means that if a third party doesn't have K-sig, right, then the third party cannot forge valid signatures, except
yeah, yeah,
for very small probability, 1 over P, something like
yeah,
this,
yeah.
right?
That's
So
correct.
in other words, if you have the K-sig, and you can either output the valid signatures or you can fake some new signatures, right? So
Mhm.
yeah, the key difference is whether you have K-sig or not. If you have K-sig, we call it designated verifier,
Yeah, that's
right?
correct.
Okay, yeah, please continue.
Yeah, yeah. So yeah, thanks for your emphasis on that topic. So yeah, for the skeptics in the room, here is how that simulation works constructively. Given R pick free K prime star, A epsilon D epsilon B from F B star, and just set the sigma 1 star to sigma 5 star using this equation. And we will see that verification still accepts. And honest signing uses K prime as the HMAC of M, and the simulator chooses any K prime star like this. And the equations only check that Shamir shares are internally consistent, not that K prime star came from a signer. So why this is a privacy feature? So, oh, sorry. So yeah, only the designated verifier can simulate accepting, and third parties cannot tell whether the sigma star comes from the signer or from the DV. So this is in the case a non-transferable proof. But anybody have the receipt can also generate the a signature. So you can transfer your verification capability to other people. So that simulation property also tells you why a standard EUF CMA or existential unforgeability under chosen message attack will not work for security analysis of our scheme. And instead, we introduced a new notion called unforgeability for everyone except the DV. And we denote it using uh, this notation. And in the game of this notion, public W0 and W1 are given, and we have a signing oracle access, and we want to forge a fresh M star and sigma alg star. And here DV is excluded from for participating in this game. So anybody can attend in this game. Instead, the designated verifier. So here we have some trapdoors, and these hidden trapdoors are nonce and receipt, which are unknown without knowing case sig. And we bound the forgery probability as 1 over p plus some terms that come from the access to the ROM or QROM, which are in the order of Q uh, number of queries over P or something like that. So they are still negligible terms. So we bound the forgery probability in this notion. And now breach that privacy property to something operators can care about, audit. After verify, the validator may publish receipt R, and validator can check M, sigma, L, and R. But valid does not prove the signer originated the transcript. It only indicates that this equation is valid. This is not easy for a random person. This is easy for people who have some information like receipt and nonce and these things. So for a random person, it is still very hard to generate a valid signature. And on three-party side, we can state a clean theorem as expressed here. So three-party SILMARILS implements FDS, indicated here, with advantage 1 over P for at most one corrupt party. And it is valid in classical or quantum setting. The proof idea is also very simple. It reduces to the information checking protocol, and it binds AX before information checking starts and lift to the quantum via some trace distance and some computational tools. So we don't want to talk about the proofs here. And finally, on security, a word on quantum. Our QRAM analysis avoids rewinding and forking techniques that breaks against quantum adversaries. And we leave classical distribution arguments using trace distance and CPTP contractivity features These are some quantum definition, and we don't want to go through them. With security covered, the last question is practical. When would you actually deploy this scheme? So let's leave the proof and talk about deployment and where would the operator use SILMARIL. So we want to see that how blockchain operators or blockchain practitioners can employ SILMARILs. So the question here is where SILMARIL fits. So in practice, the sweet spot is permission network with validator-centric verification and high-frequency user authentication. It is not aimed at a public bridges where anyone on the internet must verify signer identity. So this is nicely fits in a very vast majority of blockchain applications. And this is actually related to the companion work that we are still working on and propose a ledger architecture based on SILMARILs and its combination with PQ post-quantum schemes. So in this work, we provided a picture of how this fits together. We have TLS at the bottom and KSIG is derived from those sessions. And we have TDV for transaction and validators authentication. And we have consensus and SILMARILs validator receipts on top. And at the application level, we have smart contracts and other components. And our honest recommendation is for the moment using a hybrid application. So no either or application. So our recommendation is using MLDSA or SLHDSA whenever public verification and third-party non-repudiation matter. And use SILMARILs on validator hot passes where TDV plus optional receipts match your policy. And so it simply means that consider your trust model and then use your tool. So we have here the implementation and next step. So we have open source ROS reference implementation. We have constant time FP arithmetic, and we are working on ledger benchmarks and integration of SILMARILs with blockchain protocol. So the question that we still have and working on it is the formal proof of K derivation of K prime from K without exposing K. So this is something that we are still working on. And the future work will be focusing on generalizing this scheme to threshold signature, multi-signer, and also comparison with other designated verifier signatures. So here is the summary of this talk. So SILMARILs is a compact IT leverage TDV authentication. Its two-party is just the JSI designated verifier plus the notion of EUF-CMA except the designated verifier. This three-party gives us simulation security with epsilon 1 over P, and its application in blockchain is reducing PQ overhead on validator passes. So that's everything that we covered.
Yes, thanks a lot, Hassan, for this nice high-level overview, right? I believe this will be very helpful for readers to read our paper, right? After they kind of watch the video, and then it will be much easier for them, right, to understand not only the key ideas of our construction, but also like where can we position all the technical details, because this will provide kind of a map. Oh, the technical detail here, this long proof is serving this purpose, right? That is serving another purpose, and so on. For this, yeah, I really appreciate your time in preparing this clean presentation and for delivering it. So this brings us to part two, mostly by Mina and me, right? We will use the remaining like time, a little bit over 10 minutes, right, to like clarify further like potential misunderstandings and to highlight right a few important points. Okay, so question number one, as Hassan already explained, the new construction SILMARILS is not a replacement of some existing post-quantum signatures. Now, right, let's push it a little bit further. In your target permissioned chain, who is allowed to be convinced and who must remain an outsider? Mina, please.
Yes, sure. In SILMARILS, trust is layer. It's not universal. Inside a permissioned chain, the only parties meant to be convinced are the designated verifiers. Usually the validators or a known committee. They verify privately using their shared secret, and they can publish a receipt if they want to make the verification auditable. Everyone else stays outside that trust boundary. External observers only see algebraic consistency and not signer attribution. And that's intentional because the designated verifier can simulate transcripts. Anything that requires public non-repudiation, like governance, bridges, regularity disclosure, as mentioned, Hassan mentioned, it still belongs on a public post-quantum signature layer. SILMARILS is for the part of the system where validators are already trusted for inclusion and want cheaper constant time authentication.
Yeah. Perfect. So next, right, because you mentioned these receipts, they are very important concept in the construction, right? So now I want to like push it a bit further about its implication from a governance angle. Can an audit or regulator accept this message was verified if right they cannot prove this user signed it? In other words, as Hassan mentioned it before, right? Like with this receipt, it's not a proof that the signer did the work, right, completely. So, and it's more like this message was verified. So, right, and what is the relation between these two? How can an auditor or regulator accept, right, the statement like this?
Yeah. Yeah, an auditor accept this message was verified if even if they cannot prove that this user signed it, but only for the right kind of audit. Receipts certify execution integrity, not legal attribution. They show that the designated verifier checked the message and that the algebraic relations are correct. But because the verifier can simulate, receipts cannot support non-repudiation. And that's fine because many permission system already trust validators for ordering. And SILMARILS simply makes that trust explicit and auditable without dragging full PKI semantics into internal workflows.
Perfect. Next one, if we still remember a diagram from Hassan's presentation, and he showed this three-party information checking structure and this 1/p error, which looks very similar to some existing protocol, right? So some readers might wonder, what is new in this construction versus some existing IC signature?
Indeed, we contribute three things. First, we unify the algebraic core. The same minimal field structure gives us both a lightweight two-party designated verifier signature and a three-party information checking protocol. Traditionally, these are treated as separate constructions. Second, we prove unforgeability for all non-designated verifiers in both ROM and QROM model. That's new for TDVS signatures with simulation. Most designated verifier schemes stop at MAC-style reasoning, but we go further. And the third one is we lift the Fitzi simulation framework to the quantum setting using trace distance instead of rewinding and something like this. So we avoid all the classical ROM pitfalls, no forking lemma, no rewinding, no oracle programming. And the ledger interaction story is the application layer built on top of these theoretical contributions.
Very good. So next one, this verifier simulation, we emphasized a lot, right? Both in our paper and in Hassan's presentation. And we all know this might lead to some misunderstanding because this is unconventional, right? People need to spend some time and trying to figure out the implication of this verifier simulation. Okay, let me ask in this way. In one of the previous slides, Hassan presented simulation as a security feature, right, with some explicit equations. Now the question is, when would that property be unacceptable in a real deployment? In other words, when it will be bad after people understand the bad scenario, and then people can look at good scenarios. Yeah, Mila, please.
Yeah, it's a good question. Simulation is a feature only when attribution isn't required. It works perfectly for high-frequency user-to-validator authentication, validator-to-validator consensus messages, and internal consortium traffic. But it becomes unacceptable the moment you need public non-repudiation, like disputes, organizational settlement, and public bridges, or even open mempools. In those cases, you need public post-quantum signatures. SILMARILS isn't meant to replace that layer. Yeah.
Good. So next, maybe a very practical question, right? Because one important application of this SILMARILS construction is for blockchain, right? Blockchain developers might wonder what goes on chain and what goes off chain. Yeah.
For on-chain, you store the compact signature, a message, hash or reference, and the receipt if you want auditability. Even with receipts, this is far smaller than post-quantum signatures. For off-chain, you keep the TLS derived pair secret, the long-term keys, and anything that requires signer attribution. And that part must use post-quantum signatures.
Nice.
Yeah, the companion ledger work benchmarks this split. The paper focus on the primitives, not the economics.
Now, right, I hope the split is clean, right? What goes on chain, what goes off chain. Yeah, maybe another quick question. Because we have the two-party and the three-party modes, right? Both modes share the same algebraic core. And how would a system architect pick one for a given workflow?
Honestly, the two-party TVDS mode and three-party IC mode solve different problems. The two-party TDV mode is for direct signer to validator interactions. It's high frequency, low latency, and ideal for user transaction or validator hot passes. The three-party IC mode is for workflows where a message must pass through a holder who forwards it without learning the authenticated value. That fits mempool relays, brokers, or any mediate submission. So TDV is for direct pass, IC is for mediated pass, and neither replace public post-quantum signature at the governance boundary.
Very good. So this brings us to the last technical question, because we are researchers, right? We are honest people, and we want to share with others about some limitations and open problems, right, for our new construction. So that's why the question is, what should our online audience, including what is the future YouTube audience, not expect from our SILMARILS construction today?
Yeah, honestly, there are some few things. It's not a drop-in replacement for Ethereum style public verification, because it's not production certified yet. And we don't include a full benchmark table against all designated verifier schemes. Aligning model is messy, sorry. And the operational pipeline from the long-term key to derived key via TLS still needs a formal proof in some treat models, as Hassan mentioned. And the threshold variants are ongoing work, and the Rust code is a reference code supporting the stack submission and not a production library.
Wonderful. Yeah. So this ends our discussion today, right? Maybe one last thing. To Mina, right? What is the main takeaway for our audience before we officially end today's discussion?
It's a great question. The main message is match the authentication primitive to the trust structure. Universal public verification is expensive and not always necessary. For example, SILMARILS shows the information-theoretic, quantum-aware designated verifier authentication with receipts can be practical inside a structural environment, while public post-quantum signature remain essential where attribution matters.
Great. And this ends our talk today. And thanks again, for our two wonderful speakers, Hassan and Mina. And just a heads up, we will organize a workshop in August, at our 10th anniversary of blockchain at UBC Summer Institute, there. And we will offer more details about this new construction, Maybe we will show some potential real world applications. So if you are interested in this construction, if you want to work with us, please feel free to join our quantum workshop at blockchain at UBC Summer Institute in later August. Maybe see you there. Bye-bye.